There, where we just finished up, we talked about the steps to calculate an empirical formula, and a reminder that these are really the steps that you want to follow to calculate the empirical formula. If you're given, again, the percentages, you could assume 100 grams and turn them into grams. You definitely want to convert grams to moles using the molar mass, and you want to always divide by the smallest number of moles. So always when you're calculating an empirical formula, it's always the smallest number of moles. Again, as we talked about in terms of the rounding aspect of it, you really shouldn't, in a sort of textbook problem or anything like that, do any type of rounding unless it is really, really close to the whole number. So it's literally got to be missing the whole number just because of some rounding that you did in the calculation. But again, like I said, typically 0.33, 0.5, 2.25, 0.75, those are too far to sort of round to the nearest whole number. So as we talked about, you do need to find sort of a factor to multiply the entire empirical formula by to do that. So why don't we try one here? So take a few minutes, and we want to calculate the empirical formula based on, for vitamin C, that is 40.92% carbon, 4.5% hydrogen, and 54.5% oxygen. And again, I'm going to give you some numbers that will be helpful here. So carbon 12.01, hydrogen 1.008, and our oxygen 16. All right, take a few minutes, follow those steps we just talked about. Convert to grams, grams to moles, divide by the smallest, and see what you come up with. Okay, let's take a look and see how we're doing. So once again, the first thing we want to do is they gave us really the percentages of each of these elements by mass. You just want to quickly take a look and make sure it does add up to about 100. And again, just quickly looking, it is about 100%. Obviously, if it does not add up to 100%, you're missing somebody, right? So you're missing one of the elements that would be there. In this case, we could assume that we have 100 grams. And what that essentially is going to do is just simply change our percentages into grams. So we would have, instead of 40.92% carbon, we would have 40.92 grams of carbon. We would then have 4.58 grams of hydrogen and 54.50 grams of oxygen. So we're basically just going to turn those guys into grams. The next thing we want to do is convert to moles. So we're going to go to the periodic table, get the molar mass for each of these elements. So that's 12.01 grams per mole for carbon. That is 1.008 grams per mole for hydrogen. And lastly, that is 16 grams per mole for our oxygen. That is going to get us for carbon, 4092 divided by 12.01. We'll go with 3.4072 moles of carbon. For our hydrogen, 4.58 divided by 1.008. Going to get us 4.544 moles of hydrogen. And lastly here, 54.5 divided by 16 will get us 3.406 moles of oxygen. In this case, what we want to do is divide by the smallest. We basically have a couple of 3.4s. So we'll go with this guy on the bottom. We're going to divide everybody by 3.406. That's going to give us 1 there. That's going to give us 1 there. That's going to give us 1.33 here. Any questions so far on that part of it? Yeah. You don't in this problem. So in this problem, you could just do it like a normal calculation. We're technically doing dimensional analysis here, and this part of it, the front part, is kind of dimensional analysis. It was the smallest number of moles. So when we're ready to divide, what we want to look at is each of the moles that we just calculated, and we want to divide by the smallest number. And in this case, That was just barely the smallest number, 3.06 versus 3.407. So that was the smallest number. But once you convert into moles, that's definitely what you want to look at is the numbers that you got, and whichever one's the smallest, everybody gets divided by the smallest number of moles. Is that the same question or a different question back there? Other questions? So at this point, I'm just gonna, what am I gonna do? I'm gonna maybe go back this, there we go. That way I can write towards the top. Yes, question? We will get right there in just a second. So our empirical formula at this point would be CH 1.33 and O. And as we talked about, we cannot have sort of a decimal there. So as Aiden said, we do need to multiply it by a number to get us to a whole number. That number would be 3 would work. Again, if you took 1.33 times 1 is 1.33, not a whole number. 1.33 times 2 is 2.66, not a whole number. 1.33 times 3 gets us 3.99, which is close enough to 4 in this case. So the factor we would want to multiply is by 3. And again, it's important that you're actually multiplying everybody by 3, not just the guy in the middle. So everybody would get multiplied by 3, and that would give us C3H4O3 as our empirical formula. So once again, convert to grams, convert to moles, divide by the smallest number of moles, and that's again how you get to your empirical formula. Any questions on that calculation there? Okay, so let's try maybe another one here. What is the empirical formula of an analysis of a compound that was 1.078 total mass, made up of 5.54 grams of sulfur and 0.538 grams of oxygen, sulfur being 3207 on the periodic table, and our oxygen still being 16. All right, you give us the grams of oxygen. They also give us a third gram here, and that grams is the total mass of the compound. And that should be made up of the sulfur, and it should be made up of the oxygen. We could verify that by taking both of these numbers and adding them together, and it should equal this number. So that's just really what the number is there for. If we added those two numbers together and it didn't add up to that number, then there's probably some other element involved. But in this case, if you add those two numbers together, it does equal 1.078 grams, and just makes you feel like, you know, you got the 100% of what's in there at this point. So we really actually don't need to use the 1.078 in this sort of problem. It's just there to verify it. By the way, if it just happened to give you just the mass of the sulfur and not the oxygen, but told you oxygen was involved, you would take the 1.078 and subtract it from the mass of the sulfur, and then that would give you the mass of the oxygen that was there. So sometimes you're not maybe given the percentages, but the mass of the compound, and maybe they give you the mass of each element, or maybe one of the elements or two of the elements. So you may have to do some subtraction to get to the missing element. So because that does add up, we basically could go into our grams to moles part of the calculation, because that is where we're at. So we're going to take each of our grams of the elements. We're again going to divide by the molar mass from the periodic table for each of them. And that's 16 there for our oxygen. That's going to give us for our sulfur 0.540 divided by 3207. Gets us 0.01684 moles of sulfur. And for oxygen, 0.03363 moles of oxygen. At this point, once again, we're going to divide by the smallest number of moles. In this case, it's actually sulfur. It looks like the smallest number. So we're going to divide everybody by the sulfur number. That obviously is going to give us 1 for sulfur. And when we divide it to our oxygen, that's essentially going to give us like 1.99, depending on where you round it, or maybe a little bit over 2, depending on where you round it. But that pretty much is close enough to round to 2 in this case. That would then give us obviously our empirical formula here of SO2 in this case. Any questions on that one there? So again, this is a situation where definitely close enough to round. And again, even if we got like 2.001, it would also be close enough to 2. All right, one more here. What is the composition of adipic acid? 49.3% carbon, 6.9% hydrogen. And all right, so let's take a look here. We have our percentages. They do add up to about 100%. So we are just going to convert out into grams. So we'll assume 100 grams. So that'll give us 49, try that again, 49.3 grams of carbon. That would give us 6.9 grams of hydrogen and 43.8 grams of oxygen. Once again, we're just going to convert into moles. So 12.01 for our carbon, our 1.008 for our hydrogen, and our 16 for our oxygen there. Going to get us here 49.3 divided by a 12.01er is 4.1049 moles of carbon. We then have 6.9 divided by 1.0008 gets us 6.8452 moles of hydrogen. And lastly here, 43.8 divided by 16 gives us 2.7375 moles of oxygen. In this particular case, it looks like we're going to be dividing by our oxygen. So that is what we'll do here. Get rid of some of this up here so it's bright a little higher up. All right, so we will take our oxygen and divide everybody by. So that's going to be 4.1049 divided by 2.7375 for our carbon. We will then take 6.8452 and divide it by 2.7375 for our hydrogen. And lastly here, obviously this guy will equal 1 when we do that. Divided by 2.7375 moles for our oxygen, which would equal 1. For our other guys here, we get 6.8452 divided by 2.7375 ends up being 2.5, and here 4.1049 divided by 2.375. I think I wrote the wrong number there. Try that again. 4.1049 divided by 2.7375. There we go. Also gives us a 1.5, if I'm not mistaken. Yeah. So we end up here with C 1.5, H 2.5, and oxygen 1. We all same page? Yeah. Okay, make sure I didn't mess up. In this case, obviously we got 0.5 on both of them, right? So to clear the 0.5, we can multiply by 2 in this case to do that. This will take care of both problems, obviously. So when we do that, 1.5 times 2 is 3, I think they call that. That is 5 for our guy here, and then that would be 2. Yeah. So basically the factor there we would want to multiply by is 2 to, again, clear our decimals in each case. Any questions on that particular one? So again, this also demonstrates, you may not hit whole numbers on all of them, or maybe multiple ones that are not whole numbers, but usually you should be able to clear them with the same sort of multiple when you have to multiply by. Question on how to calculate empirical formulas here. The next thing is how we calculate molecular formulas. And really, to calculate the molecular formula, you pretty much need 3 things. You need the empirical formula. You need the molar mass of the empirical formula. And lastly, you need the molar mass of the compound. The good news is number 3 is usually given to you. So number 3 is usually given to you. Somewhere in the problem, they'll say This compound has a molar mass of like 125 grams per mole. They may even give you like a range, like the molar mass of this guy is somewhere between like 90 and 100 grams per mole. So they may give you a range. If they happen to give you a range, what you would do is you could choose anywhere in that range, the low end, the high end, the middle part of it, and it'll come out about the same. The empirical formula may be given to you, or if it is not given to you, then you need to calculate it like we were doing. So obviously, if it was not given to you, you would first need to calculate the empirical formula. So either you calculate the empirical formula or they give you the empirical formula. Once you have the empirical formula, you're going to get the molar mass of it. And then basically what you're going to do is take the molar mass of the compound, which is again usually given to you. You'll divide it by the molar mass of the empirical formula, which you may have to calculate, and it will give you a number. So let's just say we did this and that number was 2. You would take your empirical formula, and let's just say that this was my empirical formula, and you basically would multiply your empirical formula by 2, and that would give you A4B10 in this example, and that would then become your molecular formula, if this was our empirical formula. So the one place where it's kind of okay to round, even if it might not be really close to the whole number, is in this situation when you're calculating this factor, because the molecular formula and the empirical formula are related to each other by a whole number ratio. And sometimes this stuff is like a range of molar masses or something like that, or an approximate molar mass is not really the maybe perfect exact number. It is okay here when you're doing this division right here to typically round to the nearest number. So that's okay on that one spot to always sort of round to the nearest number because it really should be a whole number multiple of the empirical formula. Any questions on that one there? So let's take a look at this in action here, maybe. All right, so the empirical formula here of acetic acid is CH2O. What is the molecular formula if the compound has a molar mass of approximately 60 grams? So in this case, when we want to calculate the molecular formula, we need 3 things. We need the empirical formula, which was already given to us, so we already have that. Again, if it was not given to you, you would have to calculate it. We need the molar mass of the empirical formula, so we need to calculate the molar mass of this guy, and that would be 12.01 for our carbon. That would be 2 times 1.008 for our hydrogen, and then we would add 16 for our oxygen. That would give us a molar mass of our empirical formula of 12.01 plus 2 times 1.008 plus 16 of about 3003. So now we have the empirical formula, we have the molar mass of the empirical formula. The third thing that we need is the molar mass of the compound, and that right there was given to us as 60. So basically what we're going to do is take the molar mass of the compound and divide it by the molar mass that we just calculated. And in this case, we do end up with about 1.998, which is pretty close to 2. That means that we're going to take our empirical formula here and multiply it by 2. So when you do that, that is C2H4O2. And that would be our molecular formula. Sometimes people do, and I don't know, not a lot, but sometimes people, especially with molecular empirical formulas, so sometimes put the empirical formula in parentheses and the little number on the bottom. I personally think you should distribute it out and kind of do it that way, but you'll sometimes see it written on top left there. So again, we're basically just trying to find a factor to multiply the empirical formula by to get to our molecular formula. Any questions on that step there? All right. All right. So I tried one, you try one. Here we go. What is the molecular formula of this compound? It's made up of 1.52 grams of nitrogen, 30.47 grams of oxygen, and the molar mass is somewhere between 90 and 95 grams. So again, this is a range, so you could figure it out. Nitrogen, once again, 1401, and oxygen 16. All right. So again, remember the three things you need: empirical formula, which is not given to you in this case, so you need to calculate it, the molar mass of the empirical formula, and the molar mass of the compound, which is given to you as a range. So again, you could choose the low end of the range, high end of the range, or middle of the range when you do your division. All right, see what you come up with here to come in. Okay, let's take a look. So once again, we do need to calculate the empirical formula, so that's a good place to start. So we'll take our 1.52 grams of nitrogen. We're going to convert it into moles. We're also going to take our 3.47 grams of oxygen, convert that guy into moles as well. That's going to give us 1.52 divided by 1401, 0.1849 moles. I feel like I missed a zero in there. I did 0.8. There you go. 1.0, or not 1.0. I should just go take a nap. Hang on a sec here. I think I'm here. Hopefully I'll find my car later. All right, let's see here. Let's try this again. Let's go with 0.10849. I think there we go. Moles of nitrogen, 3.547. I don't know, whatever number it says there anymore. 0.2169. Maybe I do need to take a nap. All right, so let me super zoom because that's going to help. All right, so at this point, we do want to divide by the smallest in this case, which is that one I butchered 3 times. This number, 0.10849. Also do this guy by that as well. Going to give us a 1 there, and I believe a 2 on that one there, basically. Again here, 1.999, which again is obviously close enough to 2. That means that our empirical formula here would be NO2. Any questions up to that point there? At this point, we do need the molar mass of this guy, so might as well get that right now. That's going to be 1401 grams per mole plus basically 2 times 16. Going to give us 32 plus 1401, 4601 grams per mole. Now, in this case, like I said, they did give us a range for the molar mass of this particular compound. So you really could choose anywhere in that range. So if you want to split right down the middle there, you could go with obviously that would be the number there. Thank you. 92.5. As I erased it. Where'd it go? There you go. Come this way. There you go. We could go with 92.5. So I'll get rid of some of that so I can write up a higher here. Right. So if we took in the middle there at 92.5 and divided it by 4601, we would go 92.5 divided by 4601, gets you about 2.01. If we went on the high range, which was 95, and divided it by 4601, you would get like 2.06. And if we went on kind of the low range there, 90 divided by 4601. And again, you don't have to do all 3 of these, but just to show you that approximately they are pretty close to all 2 basically. So you could choose anywhere in that range. They're all pretty much going to be 2 as your sort of factor. So again, because they are sometimes a range, you could choose any of that. We then would multiply, obviously, our guy here by 2, which would give us N2O4 as our molecular formula. Any questions on that one there? So empirical formula, the steps that you follow to get to the molecular formula, you really just get the molar mass of each of those things and divide it out, get your factor to multiply everybody by. Any questions on how to calculate empirical formula or molecular formulas? All right, we will stop there for now.